So when you use this equation here, this is what you're going to be using. PV equals nRT. So does everybody know what all those symbols stand for? You got questions on any of those? Pressure is going to be measured in atmospheres. And it's ATM. Now, all an atmosphere is kind of an easy way to determine according to our regular atmosphere right we have now. So right now on my ears, the pressure on my ears or my body is about 1 atmosphere. Really, really close to 1 atmosphere. Does that make sense? So all the air pushing in all directions, that is 1 atmosphere. If we go down in a pool, about 10 meters, that adds on 1 more atmosphere of pressure. That's similar to 1 atmosphere of pressure. So as you go down to the pool, as your ears kind of build up pressure, you can feel it internally. Okay, you should be able. If you go down the pool, you'll feel that. So if you go down 30 feet or 10 meters, that's like 1 atmosphere of pressure adding on. And if you go down 60 feet, that's adding on 2 atmospheres of pressure. Okay? So an atmosphere of pressure just measures the number of collisions. And the more collisions that you have, the more particles you have, then the more pressure. So you should kind of understand what an atmosphere, 1 atmosphere represents. And if it's 10, it's 10 times the pressure in this room. Volume is going to be a liter. So this is about a liter. Okay? So that's about 1 liter. So there's a gas in here, and it's oxygen gas, and it's in a container of about 1 liter, is what that is. All right? The moles is how much can we pack in here. And how much, so the more we put in here, what happens to the pressure? It increases. It goes up. So it increases so much that it's a liquid in here. It's no longer a gas. That's why we can push the molecules closer and closer together, and eventually they can become a liquid. If you push them too close together, they're no longer a gas. And then temperature has to be measured in Kelvin. All right. This says for this not to get above, I think 125 degrees Fahrenheit. So that would be something way warmer than a normal day in the summer. Okay? So that's all the units that you have to do, and this is the equation that we're going to use. So this is what I'm going to have you do, and it's really easy, I think. I didn't have any complaints 5th period. What you're going to do, I'll do the first one for you, is what you're going to do is you're going to go ahead and say pressure is equal to what? So what we're going to do is we're going to get pressure by itself, and so we've got to divide volume out. When we do that, P is equal to nRT over V. And that would be my setup. Does that make sense? So what I would do is I want to get a symbol by itself, I've got to divide the other symbols out. And if I divide them out on one side, I've got to divide it on the other. So what I'd like you to do is give me the equation for V, N, and T using that initial equation up here. PV equals nRT. So that's what you'll use in which to solve all these problems. And we're not putting numbers in yet, but you will here in a second. So PV equals nRT. So solve for V, N, and T. And you're using this top equation here to algebraically move the symbols from one side to the other. And you're going to be dividing them out when you move them. So go ahead and do that for the volume, moles, and temperature. So just write them in on your own, and then we'll see. So volume measures space taken up. How much space is taken up by the gas? Moles are counting all those particles in there. So if you've got moles, you're counting all the particles in there. All right? It represents how many you have. Kind of like a dozen's 12. Mole is a big number of particles. And temperature is measuring how fast those particles are moving. So when we look at a sample, we look at its pressure, how many collisions are taking place. We look at the space it takes up. We look at how many particles are actually moving around, and then how fast are they moving around. And those are the 4 areas that we look at when we look at a gas. All right. So volume, we would do just like we did pressure, but we'd cancel out the pressure, and so it would be nRT over P is what we have. So it would be nRT over P. Any questions on that? And that will give us volume in liters. And this will give us pressure in atmospheres. The moles, when we do that, we're going to divide both sides by RT. So N equals PV over RT. Questions? Now you guys are going to have to do this on your own. So if you waited for me to do it, that's fine. But you're going to have to do it on your own eventually. And hopefully, seeing all these examples, you can perform, because you can't memorize these all. Okay? There's no way you can memorize them all. What you will be given is this setup, and then you'll have to go through and solve it. So T, you can divide both sides by NR. So that gets rid of NR. So then you get PV over NR would be your calculation, and that would give you Kelvin. This gives you moles. Kelvin temperature. Okay? What do you guys? So we're going to do 3 of these. And the first one will go together, and the next 2 I'll have you do. Okay? Right, so the first one, it says, we're going to find the pressure of carbon dioxide in a 10-liter, let's say, cylinder. And the gas temperature is 30 degrees Celsius. And we find out there's approximately 5 moles of particles in there of CO2. So what we do off the side, what I like to do off the side, I'll go PV in order, nRT. And then what I'll do is I'll pick those out. What's the pressure? That's what we got to find. Okay, in atmospheres. What's the volume? 10 liters. Moles? 5 moles. R, now this R is always going to be 0.0821. It's kind of like pi is 3.14. This is the ideal gas law constant, and it's always 0.0821. And I always give that to you. So I'll give you those 2 when you have to do a problem, those 2. And temperature is in Celsius, and this has to be in Kelvin. So you guys remember what we need to do to change it to Kelvin. It was a number, it was a high number we have to add to it. 273. We're going to add that on, and so that's going to be 303 Kelvin. So we add it on, it's 303 Kelvin. So at this point in time, we're solving for pressure. So we're going to divide both sides by volume. And when we do, pressure is equal to nRT over B. Okay. I'll have you guys plug those in and see what you get. So plug those in and see what you get. Lunch.
Yeah, just toss her. Make it like $3.
Yeah. There's somebody I seen on the fines and fee list. It was like $300 and something or $200 and something.
Holy crap! What did you buy?
That was me last year. Or actually, no, sophomore year. $375.
I mean, I guess if you lose stuff in autos, yeah.
No, this is their lunch bill. That was their lunch bill. Cafeteria bill.
What?
You don't pay for one semester. That's about what it adds up to. Yeah, no, it's like $257 per day.
Well, it could be. Well, I suppose you're only supposed to get the minimum
Yeah.
when you go through if you're a negative balance.
Imagine you're going to the. Yeah, you're negative 375.
Yeah. Hey, by the way, you're. All right. So plugging this in is 5. R is 0.0821. Temperature, I have to, students will not do this, and it gets kind of annoying that they don't realize they have to add 273. Just add 273, and the reason why is because we have temperature probes and that measure Celsius. They don't measure Kelvin, and so you have to plug that in which to get it calculated right. So that'd be 303 Kelvin, and then you would divide by the volume of 10 liters. And then what that does, it gives you a pressure in atmospheres. So we're about 1 atmosphere. This tells you how much it would be compared to a regular, kind of like room temperature. And room pressure we'd have. So it'd be about 12.4 atmospheres. By the way, if you have a pop, the pressure above the pop is like 5 or 6 atmospheres of pressure. So when you open up a pop, like this, and you go, psst, lets the pressure out. There's about 4 to 5 atmospheres of pressure above the liquid. That's right above there, that gas. That gas will have that amount. So when you do that, so what it happens is, why do they put it under pressure? Why not just leave it at regular room pressure? Why do they have a pop under pressure?
Well, it's sealed anyway, so it's eventually going to build up either way.
It can, but it's normally under pressure once they get it done. What do you think?
It makes it harder so it doesn't buckle in. Right?
Could be, because when you drink a pop, if it's under regular pressure and you leave it out under regular pressure, it'll eventually go flat or feel like it doesn't have much fizz to it, right? So they put it under extra pressure so they can have more CO2 in there. Does that make sense? They get more CO2 to when you drink it, you get that fizz and that effervescent, and the flavor is better. Okay? So that's about 3 times the pressure that would be like above a pop bottle. Okay? I'm going to ask you to do this one on your own and come up with an answer. So I'm going to have you do this on your own. You can do this at the bottom of that page, of this page. So at the very bottom of the front page, do this problem. You don't have to write it out. Just go ahead and solve for. And this one you're solving for.
Number 2.
You're solving for moles. Okay, so go ahead and do that one, and then I'll come around and check your answers. So in this one, go ahead, solve for the temperature. The one earlier we did, I'll go back to that, is that the answer was 54 moles when we set it up, N equals PV equals RT. Now this one, we're going to see what temperature is not kind of a critical temperature. So again on this would go T is equal to PV over NR, and then you got Kelvin's 974 Kelvin or 700 degrees Celsius. Okay.